Hello everyone. So this is actually a talk I gave about a month ago at PyData Florence. So if any of you went to PyData Florence, you already know this stuff. So sorry about that. But I assume not, who of you went there? How many people? Right, perfect. So the topic of this talk is, does Python stand a chance in today's world of data science? And this was a keynote, so this is more like high-level general stuff. We won't get into too much detail today. And the answer is yes. So thank you for your attention. Let's go to Kozlovna. But going a bit more into it, this is what I call the buzzword bingo slide. This is all the various tools that are relevant for data science. Not all of them. This is a part of the tools that are relevant to data science. So I assume most of you know most of it. I assume nobody knows all of it because it's just too much stuff. There's various things around AWS, the tools that they have, and message processing and queues and stuff around the databases, deployment and monitoring and containers, and it's just a whole package, and it's a lot to wrap your head around. And actually what I think is happening, not just in machine learning, this is just the Python world, but there's a lot of other stuff going on in the Java world, Scala world, and R, and so on. There's a lot of different tools. And, you know, how I like to phrase this, that we're in the part of the revolution, the data revolution, a catchphrase that I'm sure you heard. And I like to parallel this to the Cambrian explosion, which is an event in the history of Earth, like 500 million years ago or something, when all the new forms of life were being created, and new body parts and so on. And in fact, there was so much going on that the people who studied, the paleontologists, they were upset with it. They just looked at a new fossil and it was, oh fuck, another phylum. Where phylum is, you have the kingdoms, the plants and animals, and right underneath is phylum, like a new body form, which is a very rare, special thing. And now it was everywhere where they looked. So it got to the point where it's annoying. And this is a bit, you know, how we feel these days. Because what we do in my company is this data science thing, and every time you open the news, you read Hacker News or a new blog post, and it's like, fuck, another database. You know, there's this stuff happening all this time. But we have to keep track of it because this is, you know, our job. Everybody expects that we know all this, you know, the latest tools and the latest technologies and so on. So we have to keep abreast, and it's a lot of work. So in this talk, I'll talk about a little bit how Python fits into that ecosystem. The company itself, like I mentioned, we deal with data science in various domains. So these are companies, media companies, cybersecurity companies, processing documents and newsletters and so on. So various verticals, but what they all have in common that we do stuff that's related to research and engineering. Some projects, they need a bit more research. So it's like this math stuff and the latest stuff. And some projects, they need more automation or engineering or scaling, so you need to build systems that are large. So different systems, different focus, but it's all in that area. We don't do web development and so on. And it's a pretty exciting field. So I would probably, so how does Python fare here? So the several axes on which we can evaluate this. I assume most people are technical, so what people care about is performance. How do things scale and how fast is stuff? But actually when you do, you know, real work, as I'm sure most of you know as well, it's not so much the performance, but how does it plug into the rest of it? How does it integrate? How can I debug it? You know, questions like that. So we'll compare these as well. But I'll start with performance because this is, you know, this is what makes the headlines when something is faster and so on and runs on more computers. That's the cool thing. Everybody likes to read. So I actually checked a few algorithms that are very common and compared them across the various implementations in the various frameworks, just to get a taste of how difficult it is and how well it performs. One of them is SVD. It's a technique which is the core of principal component analysis and so on. It's used in many different algorithms. It's not so important here. Just care about the performance. Yeah, so just SVD, some matrix, there's some compression, some decomposition of the numbers, and what it does is not so important. We'll be using a data set of English Wikipedia. Not because it used to be called big, then it was demoted to like middle class because it's not really all that big. Everybody knows Wikipedia, it's 4 million documents, 2 billion words or something. And now it's becoming kind of small, so it's coming down on the scale of big data. you know. But the redeeming quality is everybody has access to it. Everybody knows Wikipedia. I don't have to tell you what it is. You can download it and replicate it easily. So it's still a good data set for experiments. And I'll be, in this section, I'll be comparing 4 implementations. One is in Gensim, which is Python. It's a library that, you know, I maintain, let's say. Another one is in scikit-learn. Recently, they got an online implementation of PCA, which can do online learning, not just batch processing. So that's pretty good. Then it's the Mahout, or Mahout, I don't know how people pronounce it, which is a Java framework, now more recently Scala, which is like the scikit-learn of the Java world, let's say, well established. And then Spark has its own machine learning library called MLlib, and it also has an SVD implementation. So we'll check that out.
Which Python and which Java version?
Java version.
Python has different interpreters and compilers. Which one? CPython?
CPython, the standard one, yeah. Right, so Gensim. In this graph, the red thing is how much memory it took, and the blue thing is how much time. So it was like 2.5 hours to do the decomposition on Wikipedia, and about, I don't know, 3 gigabytes of RAM, something like that. So that's just a baseline, let's say. The algorithm in scikit-learn, not as optimized, but works very nicely. You see the numbers here, it takes, you know, it requires much more time. But actually it was pleasant to work with. Like, I assume this is just a matter of optimization. So again, pretty good. Not much to say. Scikit-learn, great library. Now we're getting to Spark. So I assume everybody knows Spark, unless you've been living under a rock. But for those of you who don't, it's like a distributed memory system. You have memory distributed across several machines, and there's a protocol of what happens when something needs to be updated, like recomputed. It's essentially it. It's something, some node fails, how do you put the data back in? That's the core of it. Back when I, you know, tested this, the latest version was 1.3. Now it's a bit later, so maybe some of the stuff is outdated. And a small cluster of 4 machines, so this is distributed. And this is the result. In case you can't read it, this is a stack trace, so it failed. And of course, when this happens, you just Google for why and so on, and people already found these issues. And it turns out that it's when it's too large, the decomposition, something fails. There's an overflow and it fails. So that wasn't, you know, I can't give you the numbers for this, so it didn't work. So first glitch. Then I looked at the Mahout SVD. It's a library with a lot of heritage. It's been around. It's pretty mature. Now they're trying to, you know, move it to Spark, re-implement in Scala, and so a lot of changes happening there. How many of you use Mahout? Okay, so this is more a Python crowd, I guess. So one guy, but he's just scratching his head, so no. And this is the result. So the distributed doesn't work, so I tried the local version because I was getting desperate, you know, I can't just say nothing works. So I was trying different stuff. But then the local mode on just a single computer, it just eats up all disk space. It just does some caching or some spilling of the intermediate results, and then it fails, so another failure. So I moved to another algorithm, again, something that's popular, and a lot of people have implemented this, and I know this algorithm well, so that's why I chose it. When something goes wrong, I can just go in and, you know, maybe try to fix it or something. It's not a black box for me. If you don't know, again, this is an algorithm that takes a bunch of text and as the output, it spits out some vectors. So computationally heavy algorithm, and it's been implemented in a few. The most high profile, I would say, is the C one, the original by Tomáš Mikolov. Then my implementation from Gensim. Then there's one in Spark. MLlib also has an implementation, and there's something in Java called, you know, Deep Learning 4J. It's a library tool with several implementations. One of them Word2Vec, again on Wikipedia. I think I actually gave this talk here last time, so I won't bore you with this. It's probably online. So these are the optimizations I did in let's say, Python, but some of the hotspots were optimized, so it's actually I've spent a lot of time optimizing it, so this is not like a generic optimization in Python where you just write loops and so on. So in the end, it's faster than what you would expect from let's say a NumPy implementation. It plays well with the rest of the Python ecosystem and so on. So let me skip through this. Can talk about it later if you like, but the point is the original implementation is very fast, uses very little memory, like 2 gigabytes for the entire thing, 3 hours. The Python one, about the same time, like 3 times more memory. Okay, so demands more. And then we move to the Java world. And this was getting really annoying because I wanted at least something to work, so you wouldn't believe me. So what I did next is, again, people know about this, it's all sorts of exceptions and so on, with large models. So what I did is I scaled down the problem, so it would run on the large-scale Spark system. So what I did, there's like a parameter which says how many words can we use, do we want. So you can prune words that are not common and so on. So I increased this parameter so the model was smaller, the data set was like 4 times smaller, and then it ran on Spark. So I can show you some results. So this is it. So this is the problem that is 4 times smaller, and it takes about 3 times longer. So, so it's about 12 times, assuming it scales linearly, it's 12 times slower than the single machine implementation in C or Python. And this is actually pretty reasonable. Like, you shouldn't do distributed computing if you have a cluster of 2 computers or 4 or something. So it starts usually at this at larger numbers. So it's a reasonable thing. So works well. I assume they will fix it. This is not like a stab at MLlib. It's a new library and people are improving. Maybe it's already fixed now. I didn't check, but I guess the message here is, with these libraries, when they're new, we just have to be more careful. This is the big point for Python, because its ecosystem of its libraries is really vast, and it's been done and used in many different scenarios, and it's usually optimized, and it integrates well with other stuff. It's not as new. It doesn't make the headlines as much, but it works well. And finally, the deep learning for J, I just Googled for whether it works. I wanted to save myself the trouble of installing it after seeing the previous stuff. And sure enough, it says that it gets stuck in infinite loops on a bigger corpus. When David Tibila of IDEO, a cool guy, he did the Spotlight editor and so on, very nice stuff. So when he was checking them, he just found this. And then for Spark, he realized the same thing I ran into, that if the model is large, it just fails. So this wasn't very good, but the point here is not, that the other stuff doesn't work. My point is that you would assume people try these things. It's not just a word count example, but you just try Wikipedia or something and you find this out. This is a little embarrassing, in my opinion, just releasing, code of this quality. But just little anecdotes. So another little anecdote here is with the libraries for similarity search. Maybe some of you saw this on my blog, but I did a benchmark of these. Similarity search is, you have a vector and you need to find other vectors which are similar. That happens all the time. You need it in recommendation systems, and so it's a very common task, just like SVD, one of the core problems of this domain. So what I assumed would happen is there are a bunch of libraries that make various trade-offs. Maybe they have, they use an approximative algorithm, so they get the results faster, but maybe sacrifice a bit of accuracy, so they're less accurate, but maybe they're fast, so there would be, some library that acts like this, time versus accuracy, like these different data points. And when I actually did the benchmark on a larger data set, it happened exactly the same thing happened. Like most libraries that I tried, like half a dozen or I don't know, 10 different libraries, most of them you couldn't install. There were problems, exceptions, all sorts of things. So actually there was a single survivor this is a library by Spotify, it's called Annoy, an interesting name. But that worked really well, like you would expect. Parameter, you want less accuracy, it's faster, more accuracy, it's lower. Perfect. There's Flan, which is like the standard, but as you want more accuracy, it just fails. It just enters some infinite loop or something fails. So let's say 1.5 survivors. So this is a common pattern with practical computing. And this is a big point for Python, that it has these tools which do one thing, and they're not based on somebody having an idea and trying to sell some academic insight, but it's really people who needed to get something done, so they did it and they used it and they tuned it and so on. So it's mature. And at this point, maybe one little warning, not connected directly to Python, but how many of you know Weka, the Java library? It was popular around the turn of the century. Yeah, quite a few people. Yeah. I also contributed some optimizations there many years ago, 12 years ago. So what happens is these frameworks, they just tend to get more and more functionality and cover more and more use cases, and eventually they just implode because they're for everybody, and that means they're for nobody. So when I look for tools that help me, deliver projects that do pragmatic work, I look for tools that just do one thing. They are very focused, and they're developed by a small core of people who know their stuff, who can reply to bugs and so on. And if it gets too big, it's just a sign to move away. For me, a lot of people like it. Everything's under one umbrella. Everything fits together. It's really pleasant when it works. But when it doesn't and something fails, you just have to move through the layers of abstraction, and just adds more problems. Yeah, just an XKCD comic, like there should be one in every presentation. So let's move to the other stuff. So that was just the performance. In my opinion, if you know what you're doing, Python is great because of this heritage. But where it really maybe doesn't do as well is the more enterprise stuff, because Python comes from, at least the data part of the PyData part comes from academic background, so it's a lot of stuff that's put together so it works, and it's tested for that one domain, but there's not as much interoperability, like how do you deploy it, how do you put stuff together, and so on. So this is a picture of the ecosystem of Python in terms of installation and package management. So I guess these names: setup tools, distribute, pip, easy install, eggs, and wheels, and it's all a bit of mess. And then there's Python 2 versus Python 3, usually a fun topic. Yeah, I could say a lot about it, but let's skip it. In Java, it's a different mentality, so it can be challenging, like these things, but once you get used to it, it's fine. It's just a different mindset. It's more integrated, I assume. Again, you know how these things work. But what's important here is that the distribution is a kind of a game changer, because here what you see here is just Java heap space happens, something runs out of space. But when you have a distributed system, then what is it that actually runs out of space? You have the workers and executors and cores and containers and drivers. So and how does it actually map to the operating system, which runs with processes and threads? So what did actually run out of space, and how do I fix it? Which configuration is it, and so on? So there's like an extra level of headache in deploying this system. So it's not great in Java world either, but it's usually better. And then it never happens that you have one framework to rule them all. Many frameworks would like that. It's the bad sign, like I said, but it actually never happens. So you always need some bash scripts and copying files and cleanup and so on. So this is the task of orchestration, very important in projects. Java does it very well, has a bunch of different libraries for this, the Java world, I mean. But in Python, actually, recently it also acquired some Luigi, again by Spotify, by Eric, the same guy who wrote the nearest neighbor, the similarity search library. Very nice and clean thing, library that does one thing. I like it. So this is a screenshot from that. So you can imagine this, if you never used it, you have a bunch of tasks and they depend on each other. So these three need to finish, and then I can copy file somewhere and run something else. Not in Python, in Java or whatever. This is like a workflow management tool. And also Pinterest released their own Python library recently, like 2 months ago, Pinball. Never had a chance to look at this. We used Luigi. We also contributed some Spark, so it can run Spark jobs now. Pinball, we never used it, so I can't tell you much about it, but it looks nice. So Python, not bad, but the Java world much more mature. They've been in the game for a longer time. Logging, my favorite topic. So with logging, again, the tricky part here is doing it for the distributed cluster. So I don't know if you ever tried to debug pig scripts running in a cluster, but that's really a pain. Like if you want to see the log of what's happening on the worker nodes in pig, you just have to track the job ID and then go to the UI, the web interface, and somehow click. I even forgot already how you do it, but there's a way to get to the log actually, but it's pretty complicated. It's like a second thought, like nobody really cares, which is not true at all, especially for data science. Maybe it's true if you're just processing logs, you know, and it's a pretty standard thing, but with data science you always need to build insights and you need to know what's happening in each part of the pipeline. Yeah, when something goes wrong, you need to be able to go and see it in context. So this is very poorly done. It's also very poorly done in Python, in my opinion. So this is a part which, you know, the tools fail all around, in my opinion, and there's a huge potential for improvement. So what I advocate here, you know, when we do projects and so on, is always to sprinkle your data pipeline, the flow, with these little statements that tell you what's happening at that stage. So it's a bit like the head command in Unix. You know, you do head file and it gives you the first few lines just so you get a feeling of what's in it. So the same thing can be done with logs, and it can't be really replaced by automated computers. You could say, okay, I know this at this point there should never be an image. There should be text coming in, and I want to tokenize it. So if an image comes in, that's an error. That happens a lot. Yeah, you never look at some people never look at what's happening inside. They look at the end of the pipeline. Oh, we get accuracy 0.55. That's cool. But then you actually go in and you see all the garbage that goes through. They never check. So you see the images going in, just tokenize a binary file, you know, split on white space, and you know, what can come out of that. And for this particular example, you can say, okay, let's put an assert or like a check that this doesn't happen, but there's like a million things that can go wrong with these systems when you're doing the exploratory phase of data science. And you can't think of them all in advance and put all the little checks in there. So it's really important that a human can have a look at what's happening, put a little hat in there, see what's going through the pipeline. It always gives you surprises, okay? You just think, oh, this cannot happen, but it's not just that images go in, but maybe encoding is broken and stuff that you never thought of. So this is really it helps a lot. It saves a lot of time and improves the quality. It's, you know, garbage in, garbage out. So logging, important. Usually most tools fail, especially the distributed ones. Another pattern I noticed, I think this is coming from Silicon Valley. You know, it's like go big or go home. Everybody's trying to be as big as they can, just have an idea, but it's already, you know, disrupting the entire world and so on. And the same thing is reflected in the tools. They all often claim stuff. They're not mature. They're like pre-alpha, but they're already doing this and that. So you have to be careful about that. And I kind of, you know, after a while, you learn that you have to take it easy with these statements. So what I do is just, it's like in love. You let it go, and if it's any good, it just comes back. So I don't pay, this is maybe horrible to say, but I don't pay that much attention to all the new things coming out. It's part of my job to know them, but I give it a bit of time, both in terms of tools and in terms of academic progress. Because what we do, it's a lot of research and a lot of new papers coming out all the time. It's called publish or perish in academia. And it's the same thing. If it's any good, I will hear about it again. So I can't just spend all my days reading new papers and so on. So maybe this is a pragmatic advice, not directly connected to Python, but connected to the ecosystem of Python and other tools. So in summary, I think what I like, I'm not a fanboy of any particular tool set, so I'm not advocating Python per se, but what I really like about Python is it's the maturity from the academic viewpoint. That means tools that work, that are optimized, people who thought about how the use cases really pan out, not just sat down and just build it, but they have a problem and each they needed to scratch, so it's really well solved. The engineers, they're full stack. Some people make fun of Python. It's like a scripting glue language, it's like Bash or something. But Python actually, as I'm sure you know, has in the HPC community has a lot of really solid tools, a lot of heritage. could call it baggage, but let's call it heritage. And where it's not as good as I would say is the deployment phase, the orchestration, the pipeline management, packaging, not so good. There's a great company called Continuum Analytics. I don't know if you heard of them, but they do all these, in the Python world, they're like the elephant. They do all cool things. They have a new package manager called Conda. I'm not sure if you heard of it. Makes it easy to install the entire ecosystem and so on. They're doing the same thing they have something called Conda Cluster, I think, an enterprise offering which lets you do the same thing, this management across the cluster of machines, because as you can imagine, this is a pain. It's just a bunch of bash scripts synchronizing stuff, and it's usually a mess. So they're trying to make sense of that. So it's a really big player, and it really helps the Python ecosystem, like getting the groundwork done on how to deploy stuff, how to build stuff, how to make things repeatable. Very important. It doesn't have as much enterprise baggage, which is, I think, a bad thing, or it's a minus. Java wins there as the main competitor. Java wins there. It has the tools can be better integrated and connected to the packaging and so on. So I think that's a failure. And finally, on a more positive note, so this is the guy, the paleontologist we saw in the beginning. Every time he looked up a fossil, it was a new phylum, and he was upset. So actually what turned out later is many of these fossils which were new, it turns out that they just had them upside down. Or it was just a part of a bigger fossil, and they didn't know, they thought it's an animal, but it was actually just a part of a bigger skeleton or something. So it turns out there were not that many phyla after all. When the dust settled, it was kind of okay. And I think this is a very exciting period to be watching this, because the same thing is happening now in the data science, in the ecosystem of these tools. A lot of things coming out, hand growing out of head, and crazy stuff. But I think when the dust settles, it will be just a few reasonable tools that can be used. And it's really exciting to be watching this as these things progress. Not get too invested, especially in the new ones. They die out really quickly. Yeah. But pragmatically, some ideas like the caching thing of Spark, that's why it's taking the world by storm. Yeah. Storm is another one of their names, as I'm sure you know, but it's hard to, the space is really crowded. All the 3 little acronyms are already gone, so people are coming up with 4-letter ones. Crazy world. But yeah, it's pretty cool, and I think the same thing will happen. So that's the end of my talk. Thank you.